Alright, welcome back. I'm your friend InsectO. Today we are going to continue to learn the math because I found if I give up on this, I will probably lose some possibilities in the future. So we'll get into it. And of course, if we stop doing the practice of English speaking, we'll probably get some trouble in the future. So let's get started. Today what we are going to learn is called circles, but I guess almost large part of you guys already know what's the idea about a circle. But let's get into it again.
And with a point, let's call that point point A. And what I'm curious about is all of the points on my screen right over here that are exactly 2 centimeters away from A. So 2 centimeters on my screen is about that far. So clearly, if I start at A and I go 2 centimeters in that direction, this point right over there is 2 centimeters from A. If I call that point point B, then I could say line segment AB is 2 centimeters. The length is 2 centimeters. Remember, this would refer to the actual line segment. I could say this looks nice, but if I talk about its length, I would get rid of that line on top and I would just say AB is equal to 2. If I wanted to put units, I could say 2 centimeters. But I'm not curious just about B. I want to think about all the points, the set of all of the points that are exactly 2 centimeters away from A. So I could go 2 centimeters in the other direction, maybe get to point C right over here. So AC is also going to be equal to 2 centimeters, but I could go 2 centimeters in any direction. And so if I find the set of all of the points that are exactly 2 centimeters away from A, I will get a very familiar looking shape like this. And I'm trying to draw it freehand. So I would get a shape that looks like this. Actually, let me draw it in. I don't want to make you think that it's only the points where there's white. It's all of these points right over here. I want to draw a dashed line over there. Maybe I should just clear out all of these, and I'll just draw it as a solid line. So it could look something like that. My best attempt. And this set of all of the points that are exactly 2 centimeters away from A, this is a circle, as I'm sure you are already familiar with. But that is the formal definition. The set of all points that are a fixed distance or that have a fixed distance from A, that are a given distance from A. If I said the set of all points that are 3 centimeters from A, it might look something like this. It might look something like that. That would give us another circle. It would give us another circle. I think you get the general idea. Now, what I want to do in this video is introduce ourselves into some of the concepts and words that we use when dealing with circles. So let me get rid of that 3 centimeter circle. So first of all, let's think about this distance or one of these line segments that join A, which we would call the center of the circle. So we'll call A the center of the circle, and it makes sense just from the way we use the word center in everyday life. What I want to do is think about what line segment AB is. So AB. AB connects the center and it connects a point on the circle itself. Remember, the circle itself is all the points that are equal distance from the center. So AB, any line segment, I should say, that connects the center to a point on the circle, we would call a radius, is a radius. And so the length of the radius, AB, over here is equal to 2 centimeters. And you're probably already familiar with the word radius, but I'm just being a little bit more formal. And what's interesting about geometry, at least when you start learning it at the high school level, is it's probably the first class where you're introduced into a slightly more formal mathematics, where we're a little bit more careful about giving our definitions and then building on those definitions to come up with interesting results and proving to ourselves that we definitely know what we think we know. And so that's why we're being a little bit more careful with our language over here. So AB is a radius, line segment AB, and so is line segment. Let me put another point on here. Let's say this is X. So line segment AX is also a radius. Line segment AX is also a radius. It is also a radius. Now you can also have other forms of lines and line segments that interact in interesting ways with this circle. So you could have a line that just intersects that circle at exactly one point. So let's call that point right over there, and let's call that D. Now let's say you have a line. And the only point on the circle the only point in the set of all of the points that are equal distant from A, the only point on that circle that is also on that line is point D. And we could call that line, let's call that line L. So sometimes you'll see lines specified by some of the points on them. So for example, if I had another point right over here called E, we could call this line DE, or we could just put a little script letter here with an L and say this is line L. But this line that only has one point in common with our circle, we call this a tangent line. The line L is a tangent. It is tangent to the circle. So let me write it this way. Line L is tangent, and you normally wouldn't write it in caps like this, I'm just doing that for emphasis, is tangent to, instead of writing the circle centered at A, you'll sometimes see this notation, to the circle centered at A. So this tells us that this is the circle we're talking about, because who knows, maybe we had another circle over here that is centered at M, another circle, so we have to specify it's not tangent to that one, it's tangent to this one. So this circle with a dot in the middle tells we're talking about a circle, and this is a circle centered at point A. I want to be very clear. Point A is not on the circle. Point A is the center of the circle. The points on the circle are the points equal distant from point A. Now, L is tangent because it only intersects the circle on one point. You could just as easily imagine a line. You could imagine a line that intersects the circle at 2 points. So we could call, maybe this is F and this is G. You could call that line FG. So we could write it like this, line FG. And this line that intersects it at 2 points, we call this a secant of circle A. Is a secant. It is a secant line to this circle right over here because it intersects it in 2 points. Now, if FG was just a segment, if it didn't keep on going forever like lines like to do, if we only spoke about this line segment, let me do this in a new color, if we only spoke about this line segment between F and G and not thinking about going on forever, then all of a sudden we have a line segment, which we would specify there, and we would call this a chord of the circle. Is a chord of circle A. It starts at a point on the circle, a point that is exactly in this case 2 centimeters away, and then it finishes at a point on the circle. So it connects 2 points on the circle. Now, you can have chords like this, and you can also have a chord, as you can imagine, a chord that actually goes through the center of the circle. So let's call this point H, and you have a straight line connecting F to H through A. So that's about as straight as I could draw it. So if you have a chord like that, so if you have a chord like this that contains the actual center of the circle, a chord, so it goes from one point on the circle to another point of the circle, and it goes through the center of the circle, we call that a diameter of A. Is a diameter of circle A. And you've probably seen this in tons of problems before when we were not talking about geometry as formally, but a diameter is made up of exactly 2 radiuses. We already know that a radius connects a point to the center, so you have one radius right over here that connects F and A, that's one radius, and then you have another radius connecting A and H, of the center to a point on the circle. So a diameter is made up of these 2 radiuses, or radii, I should call it. I think that's plural for radius. And so the length of a diameter is going to be twice the length of a radius. So we could say the length of the diameter, so the length of FH, and once again, I don't put the line on top of it when I'm just talking about the length, is going to be equal to FA, the length of segment FA, plus the length of segment AH. Now there's one last thing I want to talk about when we're dealing with circles, and that's the idea of an arc. So we also have the parts of the circle itself. So let me draw another circle over here. Let's center this circle right over here at B, and I'm going to find some points, all the points that are a given distance from B. So it has some radius. I'm not going to specify it right over here. And let me pick some random points on this circle. So let's call this, I don't know what letter, let's call that J, let's call that K, let's call that S, let's call this T, let's call this U right over here. And I know it doesn't look that centered. Let me try to center B a little bit better. Let me erase that and put B a little bit closer to the center of the circle. So that's my best shot. So let's put B right over there. Now, one interesting thing is, what do you call the length of the circle that goes between 2 points? So what would you call, let me get a good color here. What would you call this? Well, you could imagine in everyday language, we would call something that looks like that an arc, and we would also call that an arc in geometry. And to specify this arc, we would say JK, the 2 endpoints of the arc, the 2 points on the circle that are the endpoints of the arc, and you use a little notation like that. So you put a little curve on top instead of a straight line. Now you can also have another arc that connects J and K. This is the minor arc. It is the shortest way along the circle to connect J and K, but you could also go the other way around. You could also have this thing that goes all the way around the circle, and we would call that the major arc. And normally when you specify a major arc, just to show that you're going kind of the long way around, the way that it's not the shortest way to get between J and K, you'll often specify another point that you're going through. So for example, this major arc, we could specify, we started at J, we went through, we could have said U, T, or S, but I'll put T right over there. We went through T, and then we went all the way to K. And so this specifies the major arc. And this thing could have been the same thing as if I wrote JUK. These are specifying the same thing, or JSK. So there's multiple ways to specify this major arc right over here. But the one thing I want to make clear is that the minor arc is the shortest distance. So this is the minor arc, and the longer distance around is the major arc, And I'll leave you there, and maybe in the next few videos we'll start playing with some of this notation a little bit more.
Right, as I guess that in that video, what he just did is tell you some terminologies about related to the circles. We get some concepts, for example, the arc, which we all or no, it's just a part of a circle. For example, if we go to Google and then we do a search about that word, what we can get? Well, for example, this image is an arc. It's just a part of the circle. Of course, we could learn some theory related to the arc, but I don't think it's necessary. If you want, you can always Google it and you'll find a lot of definitions about the arc. Why don't you spend time memory it, since you are not always dealing with that concept, or maybe in your life you will never meet it again. Okay, so there has another idea called radiance. It's probably just another unit to measure the length of arc. I guess that's it. But to be honest, let's get into it and say what it is.
What we're going to do in this video is think about a way to measure angles. And there's several ways to do this. You might have seen this leveraging
Yeah, alright. It's just another unit for measuring the angles. Or, as I would say, if you already have the angle, and then if you get the radiance, you would be able to get the arc length.
Things like degrees in other videos. But now we're going to introduce a new concept, or maybe you know this concept, another way of looking at it. So we have this angle ABC, and we want to think about what is a way to figure out a measure of angle ABC. Now, one way to think about it would be, well, this angle subtends some arc. In this case, it subtends arc AC. And we could see if this angle were smaller, if its measure were smaller, it would subtend a smaller arc. The length of that arc would be smaller. And if the angle were wider or had a larger measure, if it looked something like that, then the arc length would be larger. So should we define the measure of an angle like this as being equal to the length of the arc that it subtends? Is this a good measure? Well, some of you might immediately see a problem with that, because this length, the length of the arc that is subtended, is not just dependent on the angle, the measure of the angle, it also depends on how big of a circle you're dealing with. If the radius is larger, then you're going to have a larger arc length. For example, let me introduce another circle here. So we have the same angle measure, the central angle right over here. You could say angle ABC is still the same, but now it subtends a different arc in these two different circles. You have this arc right over here, call this arc DE, and the length of arc DE is not equal to the length of AC. And so we can't measure an angle just by the length of the arc that it subtends if that angle is the central angle in a circle, so we can get rid of that equality here. But what could we do? Well, you might realize that these two pi's that I just created, you could kind of say pi ABC and pi DBE, these are similar pi's. Now, we're not used to talking in terms of similar pi's, but what does it mean to be similar? Well, you have similarity if you can map one thing onto another, one shape onto another, through not just rigid transformation, but also through dilation. And in this situation, if you were to take pi ABC and just dilate it by a scale factor larger than 1, there's some scale factor where you would dilate it out to pi DBE. And what's interesting about that is, if two things are similar, that means the ratio between corresponding parts are going to be the same. So, for example, the ratio of the length of arc AC to the length of segment BC is going to be equal to the ratio of the length of arc DE to the length of segment BE. So maybe this is a good measure. Maybe this is a good measure for an angle. And it is indeed a measure that we use in geometry and trigonometry and throughout mathematics. And we call it the Radian measure of an angle. And it equals the ratio of the arc length subtended by that angle to the radius. We just saw that in both of these situations. So let's see if we can make this a little bit more tangible. Let's say we had a circle here and it has a central point. Let's just call that point F, and then let me create an angle here. And actually, I can make a right angle. So let's call that F, let's call this point G, and let's call this H. And let's say that the radius over here is 2 meters. And now what would be the length of the arc subtended by angle GFH? Well, it's going to be 1/4 the circumference of this entire circle, the way that I've drawn it. So the entire circumference, right here, the circumference is going to be equal to 2 pi times the radius, which is going to be 2 pi times 2 meters, is going to be 4 pi meters. And so if this arc length is 1/4 of that, this is going to be pi meters. And so based on this arc length and this radius, what is going to be the measure of angle GFH in radians? Well, we could say the measure of angle GFH in radians is going to be the ratio between the length of the arc subtended and the radius. And so it's going to be pi meters over 2 meters. The meters, you could view those as canceling out, which equals pi over 2. And pi over 2 what? Well, we would say this is equal to pi over 2 radians. Now, one thing to think about is, why do we call it radians? It seems close to the word radius. And one way to think about it is, when you divide this length by the length of the radius, you figure out how many of the radii is equivalent to the arc length in question. So, for example, in this situation, 1 radii would look something like this. If you took the same length and you just went around like this, so you can see it's going to be...
All right. So as far as my understanding, the concept of radiance is just a measure for the angle for angle. Yeah. Because no matter how long the arc you have, you always have a corresponding how they call this R. Let me say I definitely have a word for that.
Radius.
Radius. Alright, radius is different than radian. They are two different things. If you have the angle length and you divide it by the radius, you'll get your radian. Radian is a measure for angle. So with this concept, instead of having the degrees as a measure of the angle, you get the unit called radiance. Then if you know the radius, you will be able to draw your angle with exactly the length that you want. So it's probably more useful in the computer graph if you want to draw a particular angle. But in real life, it's useless because you you will probably never meet that. Okay, so what is a sector? What is a sector?
A circle with area 81 pi has a sector with a 350-degree central angle. So this whole sector right over here that's shaded in this kind of pale orange yellowish color, that has a 350-degree central angle. So you see the central angle is a very large angle. It's going all the way around like that. And they ask us, what is the area of the sector? So we just need to realize that the ratio between the area of the sector, the ratio between the area of the sector and the total area of the circle. And they tell us what the total area is. It's 81 pi. And 81 pi is going to be equal to the ratio of its central angle, which is 350 degrees, over the total number of degrees in a circle, over 360. So the area of the sector over the total area is equal to the degrees in the central angle over the total degrees in a circle. And then we just can solve for area of a sector by multiplying both sides by 81 pi. 81 pi, 8.
It still didn't tell us what is a sector. But to my best assumption, it would be just a circle without with incomplete stuff. So in other words, you got an incomplete circle.
Inscribed angles.
Inscribed angles. So holy shit. It's a quite new concept. So we're getting into it.
Circle is centered on point B. We see that right over there. That's the center of this big blue circle. Points A, C, and D lie on its circumference. We see that. Points A, C, and D lie on the circumference. If angle ABC, so that's this central angle right over here, measures 132 degrees. All right, so this is 132 degrees. What does angle ADC measure? ADC. So let's think about how these are related. ABC is a central angle. ADC is an inscribed angle, and they intercept the same arc, the arc AC. They both intercept this arc right over here. And we know from the inscribed angle theorem that an inscribed angle that intercepts the same arc as a central angle is going to have half the angle measure. And it even looks that way right over here. So if ABC, if the central angle is 132 degrees, then the inscribed angle that intercepts the same arc is going to be half of that. So half of 132 degrees is what? It is 66 degrees.
Alright, from this theory, or how can you actually give it a proper explanation on how the angle B is 2 times bigger than the yellow angle? Well, since they are sharing the same arc, which is the AC, the arc AC, the difference between the point A and B is that the point A uses 2 radius here, but the point B only uses 1 radius. So That's probably how the 2 times bigger comes from. But here we get some proofs with that. I don't want to check it. I feel sorry for myself, but I don't want to say that. Properties of tangents. It's probably a new idea or not. So, tangents. Let's get into it.
So what we have here is a circle with a center at point O, and then we have a tangent line to the circle. And let me actually label this line. Let's call this line L. And we see at point A is the point that the tangent line intersects with the circle. And then we've drawn a radius from the center of the circle to point A. Now what we want to do in this video is prove to ourselves that this radius and that this tangent line intersect at a right angle. We want to prove to ourselves that they intersect at a right angle. And the first step to doing that is we're going to feel good. We're going to prove to ourselves that point A is the closest point on line L to the center of our circle. So I want to prove that point A is closest point on L to point O. And I encourage you to pause the video and see if you can prove that to yourself. Well, to think about that, just think about any other point on line L. Pick any other arbitrary point on line L. It could be this point right over here. It could be this point right over here. It could be this point right over here. And you immediately see that it sits outside of the circle. And if it's sitting outside of the circle, I'll pick this point here just so it'll become a little bit clearer on our diagram. If it's sitting outside of the circle, in order to get from point O to this point, we call this point B right over here, you have to go the length of the radius. You have to go the length of the radius, and then you have to go some more. So this length, the length of segment OB, is clearly going to be longer than the length of the radius, because you have to go to the radius to get to the circle itself, and then you have to go a little bit further for any point that sits outside of the circle. So point A is the only point, by definition, this is a tangent line, it's the only point that sits on the circle. Every other point on line L sits outside of the circle, so it's going to be further. So point A, hopefully this makes you feel good, because you pick any other point, it's going to sit outside of the circle, so you have to go to the radius and then some. So hopefully this makes you feel good that point A is the closest point on L to the center of the circle. Now, we're not done yet. We now have to convince ourselves that if we have a point and a line, that the segment connecting the point to the closest point on the line to that original point, that's going to be perpendicular to the line. So let me give ourselves some base here. We want to prove that the segment connecting a point off the line and closest point on the line is perpendicular to the line. So what we want to do is we want to say, hey, if we have some line here, L, and if you were to take a point off the line, so let's say, you wanted a point off the line, so let's say that at this point right over here, point O, and you want the segment connecting the point off the line to the closest point on the line. So the closest point on the line, so let's say that this is the closest point on the line. We want to feel good that this segment connecting them, is going to be perpendicular to the line. That it goes just straight down like that. It's going to be perpendicular. And I'm going to prove this by contradiction. I'm going to assume that it's not perpendicular. So assume that the segment connecting, this is kind of wordy, a point off line and closest point to the line, is not perpendicular to the line. So how can I visualize that? Well, I could draw my line right over here. So that's line L, and let's say I have my point O right over here, point O. And let's say the closest point on line L to point O, let's say that it's not, so let's say it's over here, that if I were to connect these 2 points, that it's not perpendicular to line L. So this is the closest point. Let's call this point A. And let's say that the segment connecting these two is not perpendicular to the line. So let's assume that this is not perpendicular. So this angle right here is not 90 degrees. So if we assume that, the reason why this is going to be a proof by contradiction is I can show that if this is not 90 degrees, that I can always find a point that is going to be closer, another point on line L that is going to be closer to point O, which contradicts the fact that this was supposed to be the closest point. A was supposed to be the closest point on line L to O. And how do I always find a closer point? Well, I construct a right triangle. Just like this. I construct a right triangle like that. And we see that this distance, let's call this distance right over here A, unless we could call the base of this triangle B. So A, B, that's the base of the right triangle. Then the hypotenuse is the distance from O to A. We call that C. We know from the Pythagorean theorem that A squared plus B squared is going to be equal to C squared. And so B squared, if we have a non-degenerate triangle right over here, this is going to be some positive value over here. And so A is going to be less than C. So this gets us to the conclusion, because if this is some positive value here and A and C are positive, positive, everything at positive distances, then this tells us that A has to be less than C. That a non-hypotenuse side of a right triangle, of a non-degenerate right triangle, assuming it has some area, is going to be shorter than the hypotenuse. The hypotenuse is the longest side. So A is going to be less than C, which would tell us if A is less than C, then we found another point. Let's call this point, I don't know, I've used a lot of letters here. Let's call that point D. D is going to be closer. D is closer. D is closer. So we've just set up a contradiction. We assumed A was the closest point on line L to point O, but we assumed that the segment connecting them is not at a 90-degree angle. If it's not at a 90-degree angle, then we can drop a perpendicular and find a closer point, which is a contradiction to the fact that A was supposed to be the closer point. So this leads to a contradiction. Contradiction. Because you can actually find this is not the closest point. You can always find a closer point. So therefore, the segment connecting a point off the line to the closest point to the line must be perpendicular. Must be perpendicular. So the segment connecting a point off the line to a closest point on the line, that...
Alright, I guess this is not a general proof. It's just a conception, I guess. Because if OA is not the shortest part, if OA is not the shortest length, then what else could be? Only the perpendicular one is the shortest one. For others, it will always, for example, the BO, because it's in a right triangle, so it will always have a bigger value than the segment AO. Probably it's also a kind of proof, but I don't know. Maybe this is mathematics. But in the programming world, we will always use some program to prove that we are right. Constructing regular polygons in Scribe in Circle. What is it here? That's the polygons related to the concept of circles. That was unexpected.
Construct a square inscribed inside the circle. And in order to do this, we just have to remember that a square, well, we know squares, all four sides are congruent and they intersect at right angles. And we also have to remember that the two diagonals of the square are going to be perpendicular bisectors of each other. So let's see if we can construct two lines that are perpendicular bisectors of each other. And essentially where those two lines intersect our bigger circle, those are going to be the vertices of our square. So let's throw a straight edge right over here and let's make a diameter. So that's a diameter right over here. Just goes through the circle, goes through the center of the circle and to two sides of the circle. And now let's think about how we can construct a perpendicular bisector of this. And we've done this in other complex construction or construction videos. But what we can do is we can put a circle, let's throw a circle right over here. We gotta make its radius bigger than the center. And what we're gonna do is we're gonna reuse this. We're gonna make another circle that's the exact same size, put it there, and where they intersect is going to be exactly along, those 2 points of intersection are going to be along a perpendicular bisector. So that's one of them. Let's do another one. I want a circle of the exact same dimensions. So I'll center it at the same place. I'll drag it out there. That looks pretty good. I'll move it on to this side, the other side of my diameter. So that looks pretty good. And notice if I connect that point to that point, I will have constructed a perpendicular bisector of this original segment. So let's do that. Let's connect those 2 points. So that point, and then we could just keep going all the way to the end of the circle. Go all the way over there. That's pretty good. And now we just have to connect these 4 points to have a square. Let's do that. I'll connect that, and then I will connect to another straight edge there. I will connect that with that, and then 2 more to go. I'll connect this with that, and then 1 more. I can connect this with that, and there you go. I have a shape whose vertices intersect the circle and its diagonals. This diagonal and this diagonal, these are perpendicular bisectors.
Okay, interesting. It may be useful when I draw it. Sorry, I don't want to say it anymore. So this is today's learning about the mathematics and especially about the circles. Alright, I'll see you guys in the next video. Bye.